morning or good afternoon. My name is Professor Duke Orata. We are continuing with our lectures in thermodynamics. Today we want to look at how we can calculate or obtain the logarithmic mean temperature difference in terms involving these heat exchangers, because we need that mean temperature to be able to calculate the overall rate of heat transfer in the heat exchanger. Remember, we said that an heat exchanger is a unit where we have two fluids. We have heat being transferred between two fluids separated by a solid wall. And we talked about parallel flow heat exchangers and counterflow heat exchangers. And I encourage you to go through our lectures where we talk about some of these things so that we move on systematically. But in our calculations, today we will use the parallel heat exchanger. Parallel heat exchanger. Just to remind ourselves, we have the axial temperature distribution, and we had said that in this area element, which you call dA, the kind of profile which we have is such that, and this is the heat exchange area. And we said that this was dt1 this was dt2, and this is the inlet temperature difference, and we have the outlet temperature difference, and we have this is T1, this is T2, and that difference there is delta T, where delta T is T1 minus T2. And one of the things which we saw is that the fluid at the higher temperature, the fluid at the higher temperature will cool down as the heat exchange area increases, and the fluid at the lower temperature will heat up as the heat exchange area increases. So we have parallel flow. Let's just mark it so that you know what you're talking about. That's parallel flow. Now, delta T, we have said that delta T is T1 minus T2. Therefore, d delta T will be d into T1 minus T2, which is dt1 minus dt2. And if we are dealing with this parallel flow heat exchanger or a counterflow heat exchanger, remember we said the difference between the parallel and the counterflow heat exchanger is that in the case of the counterflow heat exchanger, the fluid at the higher temperature cools as the heat exchange area increases, and the same way the fluid at the lower temperature cools as the heat exchange area increases. So we have illustrated that in our earlier lectures. So let's please just go and take a look at our combined heat transfer lecture. You will find all that. Now, if we don't have any heat transferred to the surroundings, then if no heat is transferred to the surroundings, then we have the heat expression as true, where M1 and M2 are the mass flow rates for the fluid at the higher temperature and at the lower temperature. And the mass flow rates for the fluid at higher and lower temperatures respectively. And remember, what's mass flow rate? Simply the density times cross-sectional area times the velocity. We have done that in the many lectures which you have done. And the CP1 and CP2 are just the specific heats of those two fluids. And so, from this particular expression here, we can compute the change temperature for the fluid at high temperature will be basically dq or minus dq over m1 cp1, and for the fluid at lower temperature will be dq over m2 cp2. And so we can very easily use these values in that expression which we have derived earlier, so that change in temperature there, so we just put in our quantities dq m1 cp1 plus minus dq m2 cp2, which is basically minus dq, this is simply minus dq into 1 over m1 cp1 plus dq over m2 cp2. In the case of the counterflow, that will be negative. The positive there will be negative. The process is just the same. So for the counterflow, that expression will just be dq is equal into 1 over m1 cp1 minus dq over m2 cp2. Because, remember, for the counterflow, note, for counterflow, the case of counterflow heat exchanger, dq is equal to minus m1 cp1 T1, and that is equal to minus m2 cp2 the T2. And like in the case of the parallel heat flow, where that is positive, that's negative in the case of the counterflow heat exchanger. So that's important for us. So we have that particular expression, which is very important. We have that important expression, and we have this important expression. This is one. That's also very important expression. Now, if we integrate this particular expression, let's call that expression 1, or that 2, let's call this 3. So if you integrate that expression, integrate this particular expression, so it's on integration, expression 3, where we take the inlet and outlet as the limits, then we will have of delta d delta t from the inlet to the outlet, which will be minus dq 1 over m1 cp1 plus 1 over m2 cp2 which will basically, if we integrate these quantities now, will be T outlet minus T inlet will be Q minus Q into 1 over M1 CP1 plus 1 over M2 CP2. That's integrated this particular quantity. We've written it the other way around, delta T. So when you integrate that particular quantity, you simply get the difference between that value at the outlet and at the inlet. Very straightforward, because we have worked with that. And now, if we remember that we talked about, when you're talking about combined heat transfers, it means that there's a possibility that you could have simultaneous occurrence of all these modes of heat transfer occurring in a singular process. That is, you can have conduction convection and radiation all taking place the same way. So we need to talk in terms of an overall heat transfer coefficient, and that forms the basis of our earlier lectures, which again I continue urging you, humbly requesting you to go through them so that we are all together. So you remember, you will recall that we said that Q will be UA dA delta Tm, where this is the overall heat coefficient, overall heat transfer coefficient. Heat transfer coefficient. Or we can simply say Q is equals to UA A delta Tm. UA A delta T. Let's not use the main first. So the overall heat coefficient here is a function of the heat transfer coefficients for the different modes which are in that particular process, whether it's conduction plus convection or conduction, convection, radiation. Then we expect that the overall heat transfer coefficient will be as a function of those individual modes, not necessarily a sum total of the individual modes. That might not be the case. In most cases, that will not be the case, but they will all be related in one way or the other. So that if we now take that particular quantity, if we now take this particular quantity, remember we have that as d delta T. If we plug in this value for the overall rate of heat transfer, overall rate of heat transfer, then we will have V delta T will be equal to, if we put in that value there, you have U, which is the overall heat transfer coefficient, then we have A delta T into 1 over M1 CP1 plus we have minus there, plus 1 over M2 CP2. Very simple. We're just using the overall expression for the rate of overall heat transfer, where we have factored in an overall heat transfer coefficient, which we have already explained, and of course the associated areas and the temperature change. So, if we reorganize, if we rearrange this quantity, then we realize that we have d delta T over delta T, and that is equals to UA A to 1 over M1 CP1 plus 1 over M2 CP2. And of course, we already know that if we integrate that particular quantity, we have dA, sorry, let's not forget our dA. If we integrate this particular quantity, use the identity, remember we have the identity, if we integrate dx over x, that will give us natural log of x plus integration constant. So if you look at it, you see that that is similar there. That is very similar. that particular expression there. So that on integration, using that identity, we will have natural log of delta T naught, delta T naught, that is the outlet, that is the inlet, remember, will be UA into 1 over M1 CP1 plus 1 over M2 CP2. But remember that we had the expression, early expression, let's just remind ourselves, we had that early expression D delta T, which was equals to DT1 minus DT2. We had that particular expression. Remember, we had that particular expression. D, the T1, that is DT2, minus that, and we had gotten this expression as minus dq over m1 cp1 plus minus dq over m2 cp2. And we say that was because for parallel heat exchanger, for the parallel heat exchanger. That's what we say. That was for the parallel heat exchanger. In the case of parallel heat exchanger. And remember, delta T, that is T is T1 minus T2. It's T1 minus T2. So we have this as minus dq into 1 over m1 cp1 plus 1 over m2 cp2. That's delta T. So what we have here is D, therefore, of T1 minus T2 is minus dq 1 into 1 m minus m1 cp1 plus 1 over m2 cp2, where we say that the m1 and the m2s are the mass flow rates for the fluid at a higher temperature, at a lower temperature, and of course the cp's are the specific heats for those particular fluids. So what are we having here? So we have gotten our expression. We have our expression here, which is given by that. So if we integrate this particular quantity, we have T1 minus T2 is equals to minus Q into 1 M1 CP1 plus 1 over M2 CP2. 1 over M1 CP1 M2 CP2. So we can have, if we divide this quantity, that particular quantity, so if we divide, call that asterisk 1 by, where are we? Let's call it asterisk 2. So if we dividing asterisk 2 by this 1, what do we get? We will have T1 over T2 divided by natural log all delta T naught delta Ti. Remember, that is the inlet. I is for inlet. O, that's not there, is for outlet. Don't forget that. Don't forget that. And so if we do that, what are we going to get? We are going to get Q minus Q. Your minus Q to 1 over M1 CP1 plus 1 over M2 CP2 divided by overall heat transfer coefficient, area 1 over m1 Cp1 plus 1 over m2 Cp2, and of course those two will cancel out. Those two will cancel out. That's just straightforward algebraic bookkeeping. You just have to do bookkeeping of your quantities, nothing spectacular, so that we have delta T, which is T1 minus T2 over natural log delta T naught over delta T I as being equal to minus Q over rho A. So that, in a nutshell, Q here, therefore, is equals to UA A Q, we cross multiply delta T over natural log of delta T naught T I. Now, remember that we say that for the overall rate of heat transfer, just note, for the overall rate of heat transfer, Q will be minus UA overall heat transfer times area times the mean temperature difference.